Hello. Today we are going to discussing about elementary particle symmetries. So before entering this topic, brief introduction about this elementary particle symmetries. So we know that the atomic weights and other properties of unknown elementary particles were correctly predicted by using a periodic table, Mendeleev periodic table. Similarly, the classification of elementary particles also met in success predicted new particles. Uh, the method developed for predicting new particles is based on group theory. Developed for the predicting new particles is based on group theory. Okay? So this theory is proposed by the well-known physicist Ray Gilman, the American physicist, and one more physicist is there, Israel physicist, Newman. Okay, so we know that certain properties of elementary particles remains unchanged with respect to certain symmetry operation. So we already familiar this type of operations. Here I'm going to give few examples. One is linear momentum. We already know this one. The linear momentum is conserved with respect to displacement. Okay, and angular momentum is conserved with respect to rotation. And the energy is conserved with respect to the time. Mm. Second example is the angular momentum. Angular momentum is conserved with respect to rotation. So example three, the energy. Energy is conserved with respect to time. Okay. For example, we have the set of symmetry operators in which the properties are unchanged or conserved constitution a group and the group contains a number of states. So any symmetry operation can transfer any one of the states to another in the same representation. They are mainly three type of symmetry group of elements are there. The three classifications for the symmetry group for the elementary particles. One is a simplest unitary group. So this is denoted by U1. Okay. So this group consists of a transformation which add a phase factor only to the particle wave. Okay. Uh, the invariance under such transformations gives conservation of charge, especially in this group. hypercharge, baryon number, and the lepton. So this is all about the simplest tree unitary S1 group. So this is the main fact. Adding of phase vector only to the particle wave function, and the invariance under the transformation gives the conservation of the charge, baryon number, lepton number. Okay, that is SU. I mean SU1 simplest unitary group. Right. Here the next two are very important. One is unitary symmetry. SU2 symmetry. So this group, the symmetry operation change the sign of a third component of isospin. So we know that, for example, in case if I take uh, proton and neutron, two elementary particles with identical proton and neutrons are considered here. So to be identical but different in electromagnetic interactions, the two particles have the spin 1 divided by 2. The spin of proton and neutron spin, just wait, going to write like this. Okay, proton and neutron. Okay, spin of these particles is spin is 1 divided by 2, and the isospin third component, that is I3 component of proton is plus 1 divided, and neutron is minus 1. Imagine a set of symmetry operators which change proton into neutron and vice versa. So here I'm applying symmetry operators. Okay, will change proton to neutron, neutron to proton. In this transformation, spin is constant here. Spin is constant, and the third component changes the sign of coordinates. So the symmetry group, therefore, the symmetry group is which the isospin is conserved, is called unitary symmetry. Okay, it is denoted by SU2 or U2 like this. Okay, so which can be represented by 2 by 2 matrix. So in which number of operations. So how many operations are there? 2 by 2, 4, right? This group may be reduced to a special unitary group. So that is the SU2. So in which, especially in the number of operators are reduced by 1. So in SU2 group, we have only 3 operators. All the number of SU2 groups have the same spin, and the T component are essentially identical except for charge. This group consists of the 2I plus 1 states. And one more important information here. This S2 symmetry is violated for electromagnetic interaction in which conservation of isospin is violated. So this one is very, very important. So I'm going to write like this. Okay. The SU2 symmetry is violate for EM interaction, electromagnetic interaction, in which the conservation of isospin is violated. Okay, this is very, very important. So for example, here I'm going to write one equation. So the nucleon state in nucleon states the P greater than it is n actually have anti-nucleon states also. So which is denoted by like this. For example, uh, so it is better to write nucleon states P for our understanding. Okay, just in nucleon state I am going to write P and n. Okay, and in nucleon state I am going to write P bar and n bar. Okay, so this is better. The combination of nucleons and anti-nucleon states may be represented by this equation. I'm not explaining this derivation, just I'm going to write that equation. So P n, this is normal nucleon state, this anti-nucleon states. Okay, P bar, n bar. Okay, it's also normal bracket, not square bracket. Tends to, I'm going to write this equation like this: P bar plus n bar divided by root 2 1 0 0 plus P bar minus n bar to 1 divided by 2 or P n bar. This is one state. N P bar, here P bar minus n bar into 1 divided by 2. So the combination of nucleons, okay, these nucleons and this anti-nucleons, I'm going to write this equation like this. Very, very important information. This is one term, this is the another term. The first term and second term both are very important. So here the first term, this first term represents the singlet new mesons, and the second term represented pions, and the second term can write like this. So these are all useful to explain the quark model. The quark models are there. Second term only. I'm not going to write the first term. Second term is very, very important. Pions we can write like this: pi plus. This is pi minus pi naught divided by root. So remember this equation. Very, very important. So in the similar way, uh, the eightfold symmetry also there. Okay, so this is actually, so here we got four operations. Okay, and here we reduce it by the one operation. Then we have only the three operations. So like that. So in SU three symmetry also there. So this SU3 symmetry, or this SU3 symmetry, and call this one the eightfold symmetry. So this group is generalization of a isospin, and this stands for special unitary group in three dimensional, in which the operations are the 3 by 3 operations are there. So total number of operations 9. So this is reduced to special unitary symmetry, in which the number of operations are reduced by the unitary, and it is called eightfold SU3 symmetry operation. Therefore we have only 8 operations. Of the 8 operations, so out of this 8 operations, okay, one is reduced. So 3 operations are applied to the, out of this 8, 3 operations are we're going to apply isospin, the the fourth operation is up to 1 2 3 is isospin, one operation. Total 8 operations are there, 1 2 3. I'm not going to specify what is 1 2 3. So one operation, 3 operations, so we are going to apply the isospin. Then the fourth one operation is associated with the hypercharge, and the remaining 4 also involve hypercharge in different ways. So remember these things. Total 8 operations. Hypercharges in different way. So from the theory of group theory SU3, this symmetry gives 6 super multiples containing of the uh, 1, 8, 8, 10, and this anti group also there, 10 minus, and 27 number. So here the specific thing here, the number 10 minus this multiply the equal to the 10, but the hypercharge is opposite sign. So therefore the all the numbers of the super multiples and the parity and spin are the same. The uh, hypercharge and third component of isospins are not same. So this is important. So here the all the members of the super multiples, the parity and spin are same. Okay, the parity and spin are same. Hypercharge and isospin component or not same. The importance. So this eightfold way is especially invented by the American physicist. We already discussed that name of that Murray Gilman. Okay, so we already know that scientist name. So he is very famous scientist, especially Murray Gilman. He's invented this eightfold symmetry. So in case of variant 0, in case of B equal to 0, the particles and antiparticle states from 3 by 2 RS are given by this one: proton, neutron, and lambda. Proton antiparticle, neutron antiparticle, lambda antiparticle. If we try to multiply, operate these two values, then you can get this 1 divided by 3, 2, P bar minus N bar minus lambda. This P N bar, P lambda bar, N P bar is 1 divided by 3. I'm not explaining this thing, I'm not going to prove this table. Okay, just I'm writing P bar plus 2N P bar minus lambda bar. And lambda n bar 1 divided by 3. Here the two minuses. One is P bar minus n bar plus 2 lambda. So this is a important. In case if you want to identify the known spin of zero mesons, you can write this equation like this: pi naught divided by root 2 plus root 6 pi plus a plus pi minus pi naught divided by root 2 plus meson 6 k naught k minus k naught plus 2 newton divided by root 6. For example, the so this is for the spin of zero meson. Okay, the neutral meson can write like this: P bar plus n bar plus 2 lambda bar divided by 6 root 6. This antiparticle prime P bar P. In case if you interchange this operator n bar n plus lambda lambda divided by root 3. This is root 3. So here I'm going to give one note, one note. Since these mesons are formed from Fermi particles, and the anti-fermion particles interactions have odd parity. So therefore, the 8 particles with these 8 particles with b equal to 0. So we can arrange it in a geometrical way. So for example, one triplet with hypercharge is equal to 0, isospin equal to 0. One doublet, hypercharge equal to 1, isospin equal to 1 divided. So one doublet, hypercharge equal to -1, isospin equal to -1 divided. One singlet with a hypercharge equal to 0, the isospin equal to 0. So by using these conditions, we can arrange the different type of geometrical mesons. So variance, octal structure, mesons, actor structure. So these are all the important three symmetry operations, SC1, SC2, SC3. So by using, especially in SC3 symmetry operation is very, very important. uh, to find the elementary particles. So next class I'm going to discuss the geometrical arrangement of baryon and baryon baryon particles and mesons.